All right, this is assignments 26 and 27 merged together, and we're just practicing writing out Taylor series. It's also good to think about when can you just build the series and when do you have to do it the long way. So use the definition of a Taylor series to find the Taylor series centered at C for the function. So uh, anytime the center is at 0, you can build the function. So remember, we have memorized some of these Taylor series for some of these functions like e to the x. So you should know that e to the x is, I'm just going to expand out a few terms here. 1 plus x squared over 2 factorial plus x cubed over 3 factorial. I'm just going to say plus dot 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 plus. And then in general, it's x to the n over n factorial, and that goes on forever. And so this is just saying e to the 2x, meaning plug 2x in for that x. And so all you are doing is subbing in the expression 2x in for all of these x's. So, and I'm not going to simplify anything. I'm just going to plug it in. So 1 plus 2x plus the quantity 2x, the quantity 2x squared over 2 factorial plus the quantity 2x cubed over 3 factorial plus dot 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 plus. So in general, you're subbing a 2x in here and raising it to the n. And they want me to write the series, so I can now say, I like doing the terms first. I can say, okay, this is starting at n equals, it seems like it's n equals 0, right? You want to double check that wherever you start, you actually do generate those terms. And then if you have the nth term written out, it should just be the nth term here. And like I said, just do a quick check. Does this start at 0 or should it be 1 or something like that? So if you plug in 0, 2x to the 0 is 1 over 0 factorial. And remember, 0 factorial is 1. So I do get that first term. If I plug in 1, I get 2x to the first over 1. So yeah, so this is generating the correct terms. It's just good to always do a mental check of that. So there's the Taylor series. On the AP test, sometimes they will say, write out the first 4 terms and the general term. So that's what I did in the previous step. This one says, find the Taylor series. So I wrote it in its summation form. The next one is f of x equals cosine x. And we do have a Maclaurin series memorized for this, but this one is not Maclaurin. It's centered at c equals pi over 4 instead of centered at 0. So I cannot build this. I need to go and do this the long way. And how many of these derivatives do I need to take? It's just enough until you can figure out what the pattern is, really. So I always start with saying, okay, f of x is cosine x. F of pi over 4 is going to be radical 2 over 2. And f prime x is negative sine x. F prime of pi over 4 is negative radical 2 over 2. F double prime is negative cosine. So f double prime evaluated at pi over 4 is, again, negative radical 2 over 2. So definitely the number, the coefficient is always going to be radical 2 over 2. How do I get this plus, minus, minus? Let's do a couple more to see what the pattern is. The derivative of negative cosine is positive sine. So evaluate at pi over 4, you're back to positive. Let's just do one more. The fourth derivative brings us back to cosine. With sine and cosine, by the way, it's the fourth derivative that should get you back to your original function, meaning original sine or cosine. So that's going to be another positive. So we need to come up with an expression for negative 1 to the something that gives us positive, negative, positive, negative, negative, positive, positive. The next two are going to be negative, negative. I can generate more terms if I want to, but this is the question. And we had something like this in our notes earlier in the chapter. Remember, it was like n times, it was either n plus 1 or n minus 1 over 2. Let's see if this works. Double check this. So let's say the first one is n equals 0. anything to the 0 power is 1, so that's positive. If n equals 1, I should get a negative here, so it'd be negative 1 to the 1 times 2 divided by 2, so that is negative 1. Let's check this for n equals 2. You would get negative 1 to the 2 times 3 divided by 2. That's odd again, so negative. Let's make sure I get a positive when I put in 3. Negative 1 to the 3 times 4 over 2. 4 over 2 is 2. 2 times 3 is 6. Negative 1 to the 6th is positive 1. So, yeah, you can do as many terms as you need to convince yourself that this is the pattern, but I think this is going to work. So, when I write the series, I'm going to keep that in mind for my general term here. All right, otherwise, what is it going to be? I still think it's a good idea to do some of the terms here. So remember the formula for a Taylor polynomial. It's f of pi over 4, f of c, plus f prime of c. Actually, that's negative. Times x minus c over 1 factorial. We don't always write that, but we can. And then it's minus radical 2 over 2. This will be x minus pi over 4 squared. And then there's a 2 factorial here. And then it'll be plus. I'll just do one more term. Again, this problem is not telling us we have to expand out terms, so I'm just doing as many as I need to get a good idea of the pattern here, but I think I have enough that I can write the series. So our series goes from 0 to infinity because I started at 0 when I was checking this pattern. This negative 1 expression needs to be here to generate the correct odd and even term, odd and even powers of negative 1, so to get the correct signs. Every term has a radical 2 over 2. Every term has an x minus pi over 4, and it is to the n power, right? To the 0, to the first, the second, third, and they're all over n factorial. So it has some pieces of the cosine original equation, like the cosine. We had there's like a 2n factorial, but this is not the same exact equation because it's not centered at 0. So don't try to build off of the original. You can always double check the series that you write down. It's a good idea to put in some numbers starting at whatever n you have, and it should generate these terms. Sometimes we might have different expressions and start in slightly different places, but if we are all generating the same terms, then that's okay. There can be slight variations on this as long as it gives all the terms that it has to give. Okay. Number 4. So we want sine x, but again, we're centered at pi over 4. So this ought to be really similar, right? I think it's really just going to come down to we just need to figure out the pattern for the pluses and minuses, right? So let's see. So if f of x is sine x, we're starting off positive again. Okay, so f of pi over 4 is radical 2 over 2. And then f prime of x will be cosine x, so that's going to be positive again. So that's different than the previous one because the previous problem when it was cosine, we got positive and then negative right away. So right now we're plus plus. And now our next term is going to be negative sine for the second derivative. So evaluated at pi over 4, now that's negative radical 2 over 2. Okay. I'll do one more, but I'm pretty convinced this is going to go plus, plus, minus, minus. Back to negative cosine x. When you plug pi over 4 into that, you get negative radical 2 over 2. So yeah, plus, plus, minus, minus. Okay. This same expression that I had for here isn't going to work because that gave me plus, minus, minus, plus. So what if we try, it's got to be something similar. So what if we try like n times n minus 1 instead of n plus 1? See if that makes a difference. So start at 0. Negative 1 to the 0 is 1, so that's good, positive 1. And then negative 1 to the, put in 1. 1 times 0, okay, 1 minus 1 is 0. So yeah, that's going to be 0 again. That gives me 1. And then plug in 2. Negative 1 to the 2 times 1 over 2 is negative 1 to the first, which is negative 1. I think this is going to work. Let me do one more. Put in 3. Is that where I am? Yeah. 3 times 2 over 2. Yep. Negative 1 to the third is negative 1. So I think this is the correct expression. And it still helps if you want to generate out some of these terms. So it was radical 2 over 2 plus radical 2 over 2 times x minus pi over 4 to the first over 1 factorial minus radical 2 over 2 times x minus pi over 4 to the second over 2 factorial. I'm just going to say minus dot, dot, dot. I think I can get down to my series here. So it still starts at 0 to infinity. I'm going to put in my negative 1 expression so that I get the correct positive and negative signs. There's a radical 2 over 2 on this one. There's an x minus pi over 4 to the n. And it's still times n factorial. 2 times n factorial, by the way, is different than 2n factorial. So just be careful with that. It's only the n that's in the factorial. All right, number 7, ln x. So this one's centered at 1, so we should go ahead and build it again. So f of x equals ln x. F of 1 is ln of 1, which is 0. F prime x is 1 over x. F prime of 1 is 1. This isn't one that we've memorized, but we've done it a few times in the homework now, so maybe you do know what it is. The second derivative is going to be negative 1 over x squared. So f double prime of 1 will be negative 1. F triple prime is back to positive 2 over x cubed. So f triple prime at 1 is 2. The fourth derivative is negative 6 over x to the fourth. Put 1 into that, you get negative 6. I'm just going to do one more. 24 over x to the fifth. Fifth derivative at 1 is 24. If you don't remember the pattern for these numbers, ignoring the pluses and minuses for a second, the number value is compare the n, 5, to the number 24. Compare 4 to 6, 3 to 2, 2 to 1, 1 to 1. These are factorials. So 24 is n minus 1. It's 4 factorial. So it's n minus 1 factorial. And then with the positives and the negatives, it's the odd terms that are positive. So, and the first term is 0 here. So like the odd terms are positive. When n is odd, you get a positive. So we would need like a negative 1 to the, say, n plus 1 or something. All right, so ln x is going to be 1 minus 1 times x minus 1 over 1 factorial, if you want to throw that in there, plus, oh no, wait, what am I, let's see. Sorry, I skipped over the 0. 0 plus 1 times x minus 1 over 1 factorial minus 1 times x minus 1 squared over 2 factorial plus 2 times x minus 1 cubed over 3 factorial minus, I'm just building the thing, by the way, so minus 6 x minus 1 to the fourth over 4 factorial plus 24 times x minus 1 to the fifth over 5 factorial. Why am I doing so many terms? Because I'm trying to come up with my series. I figured out some of it. I figured out the f sub n part. Because remember, all of these in general are like, you've got some series, you've got some pattern for the derivatives, times x minus c to the n over n factorial. And so it's this pattern that we're really trying to figure out. All right, so the pattern was negative 1 to the n plus 1 times n minus 1 factorial. Those are the numbers being generated in the top. And then this is still times x minus 1 to the n, and it is over n factorial. And you can simplify some things here. You don't have to, but remember, n factorial is equal to n times n minus 1 times n minus 2 times n minus 3, or n times n minus 1 factorial. So you could actually simplify this. Again, we don't have to, but we could reduce these, right? 6 over 24 reduces. 24 over 120 reduces. 2 over 6, 1 over 2, 1 over 1. So this does reduce. It could just be negative 1 to the n plus 1 times x minus 1 to the n. And this n plus 1 could cancel with this factorial, and you would just have an n left in the denominator. It's good to know about this, because if this is multiple choice, then I'd be able to find that answer. But if it's free response, you don't have to simplify. All right, number 8. We're back to e to the x. C is 1, so again, we can't just build it. But this one should be a bit easier, because f of x is e to the x, and f of 1 is e to the first. And every derivative is just going to be e to the x. There's no chain rule happening or anything. So we're going to get e for every single one of these. So the formula for f sub n of x is e to the x, and f sub n of 1, is what I should have said, back there, is always going to be e. So e to the x, I don't think I'm going to do terms on this one. It starts at n equals 0 to infinity. There's always an e right here. And then the center would be x minus 1 to the n, and it would still be over n factorial. So remember, when you're doing all these derivatives and you're trying to come up with a pattern, that just takes care of the f sub n of c. I shouldn't have said 0 there. F sub n of c, part of the formula, but you always have this term here. All right, prove that the Maclaurin series, this is great because center is 0 and I can build stuff, for the function converges to the function for all x. So remember, this means that the Maclaurin series that you come up with, if you could add infinitely many terms, you would get exactly the cosine function for the entire cosine function. It's not just going to match up for a little portion of it. So to do that, we need to remember what our Maclaurin series is for cosine x. So remember, cosine x is the one that generates your odd terms. So it's like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus da da da. So what is the series? It's the sum from 0 to infinity of negative 1 to the n times x to the odd numbers 2n plus 1 over 2n plus 1 factorial. So this is x to the odd number over odd number factorial. How do I prove if this function converges or diverges? So I need to use the ratio test. We always use ratio test for this. So we're going to say the limit as n approaches infinity of the n plus 1th term over the nth term. So the n plus 1 term in absolute value is x to the, here's what I'm doing, here's the math I'm doing, 2n plus 2 plus 1. So it's x to the 2n plus 3 over 2n plus 3 factorial divided by this fraction, so multiplied by the reciprocal. 2n plus 1 factorial over x to the 2n plus 1. Things should cancel when we're doing the ratio test. So 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So that's going to cancel. These will be left behind. Subtract these exponents. 2n plus 3 minus 2n plus 1 leaves you with 2. So rewrite this limit notation without just leaving everything all slashed out. So I have x squared up here. And down here I have 2n plus 3 times 2n plus 2. And when you take the limit at infinity, yes, you have x squared, but it's x squared divided by infinity. So that is 0. And remember, the rule for ratio test is that if you get anything less than 1, which 0 is, then this converges absolutely by the ratio test. So that's why the interval of convergence will be for all, or the interval of convergence will be all x. So will be negative infinity to infinity. It's when you have an x still in your expression that you have some sort of limited radius or interval of convergence. All right, next one. Again, this is Maclaurin, so we can build this. So remember, e to the x is your 1 plus x squared over 2 factorial plus dot, dot, dot. Build into that e to the negative 2x. So we're putting in 1 plus negative 2x plus negative 2x squared over 2 factorial plus dot, dot, dot. So when we go to write our series from n equals 0 to infinity, we get, I'm just going to plug in just this. So normally I have, let's see. So normally I have like my e to the x series is just x to the n. Maybe I'll write the general term. X to the n over n factorial. But we're just plugging negative 2x into this. So negative 2x to the n over n factorial. And I think I'm just going to leave it like that for doing the ratio test. So let's see. The limit as n approaches infinity of the absolute value. So the absolute value piece just means like, so this is negative 1 to the n times 2x to the n. So just leave the negative off of this. And it would be 2x to the n plus 1 over n plus 1 factorial times n factorial over 2x to the n. So those are going to cancel, and we'll just have 2x to the first. And then n factorial and n plus 1 factorial cancel to leave you with just n plus 1. So this is the limit as n approaches infinity of the absolute value of 2x over n plus 1. This again is 2x over infinity, which is 0. So when you get 0, it means this would be true for all x values. We would still get 0 as we let n grow to infinity. So this converges by ratio test for, oops, that's supposed to be the word for all x real numbers, or from negative infinity to infinity. Okay, find the Maclaurin series for this function. Use the table of power series elementary functions. That just means, again, we can still build because these are Maclaurin, and we have a center at 0. So because we just worked with this, I'm just going to write the series for e to the x first. That's x to the n over n factorial. And so if I want to do x to the negative, oh no, not negative, e to the x squared over 2, I'm just going to plug that in. I will show you how to simplify it a little bit, but unsimplified, it would just be putting x squared over 2 to the n over n factorial. Now, if I'm looking for this answer in multiple choice, they're not going to leave it ugly like this. So just remember about exponent rules here. Keep my summation notation in there. Raising to the n power makes this part x to the 2n over 2 to the n, and then you're over n factorial. Well, that can get cleaned up. It's x to the 2n over 2 to the n times n factorial. So that's my e to the x squared over 2 series. And again, for a free response question, you can leave it ugly like the first one I wrote. But if you're trying to find the answer, it will probably be simplified. Or if you're trying to do something else with it, then it might be better to simplify it. All right, 34. same thing. We have a series for cosine. Cosine x. It is this. Negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. So if I want to create a power series for cosine of pi x, all I need to do is sub in pi x for that x right there with parentheses. So negative 1 to the n, pi x to the 2n plus 1 over 2n plus 1 factorial. Now, I might have had a simplified version of it. Oh, no, wait. Do I have my wrong? Am I messing up my cosines? Hold on. I'm looking at my answer key and it says something different. Oops. I'm using the wrong thing for cosine. Did I do that back here? Cosine is... Where did this go? On number 13, did I use the wrong series for cosine? It's the evens, isn't it? I thought it's the odds there. Oh, let me go back to my notes now. This is not great, is it? Let's see. Power series, operations, this guy. Where are the ones we have memorized? Taylor series. There we go. Taylor polynomials. Oh, here it is. Oh, yeah, sure enough. Cosine are the evens, sine is the odds. Well, I screwed that up, didn't I? So if I go back to my homework. Okay. I need to fix number 13. I'm going to get the same answer, but let me fix this because we can't just have it be wrong. That would be crazy. Boop, boop. So it's the evens. Excuse me. I'm so sorry about that. So the evens, this is the original. Oh, no, sorry. The terms were 0. So you get 1, and then you get minus x squared over 2 factorial plus x to the 4th over 4 factorial minus blah, blah, blah. All of this is still going to work out the same way. To the same conclusion, I should say. I'm going to leave my conclusion up there. Okay, so x to the 2n plus 2, because 2 times n plus 1, over 2n plus 2 factorial. 2n factorial here. We have x to the 2n here. So we're still going to have x squared. We're still going to have 2n plus 2 times 2n plus 1. Same conclusion. Which brings me back to this guy on number 34. Get rid of these odds. Sorry, I'm making this video and I have not taught this yet this year, so I'm a little rusty on it. My bad. All right. Yeah, so we're plugging this in pi x times raised to the 2n power over 2n factorial. And I would not do anything to rewrite this. I think I would just leave that as is. I don't really know what you would do to simplify. All right, for the next one, find the Maclaurin series. Again, we get to build this. And so this is x times sine x. So let's see if I can get this right. So sine x originally is our odds, right? So that's going to be the one that's 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Here's my general term. Plus dot, dot, dot. And all that we're doing, oh gosh, and this shouldn't be 1. This should be x. Goodness. Okay, so then when we do x times sine x, that multiplies every term by x. So this is now x squared. This is now minus x to the 4th, but it's still over 3 factorial. Plus x to the 6th over 5 factorial. Minus x to the 8th over 7 factorial. Okay, so when you're multiplying by x, what you're really doing is like x to the 2n plus 1 times x to the 1st. You're just adding these exponents together. So this is still negative 1 to the n. This is now x to the 2n plus 2. And this is still over the odd factorial. So find the series. I just need to write the same thing in a series form. So x sine x is equal to the sum from 0 to infinity of negative 1 to the n, x to the 2n plus 2 over 2n plus 1 factorial. And I can do the same thing with cosine. And I think this is our last problem. So let me see if I can get this right. So cosine is the one that's 1 because that's like x to the 0 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot 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 plus negative 1 to the n x to the 2n over quantity 2n factorial plus dot dot dot. And if we want to multiply everything by x, let's see what that does. So that makes this x minus x cubed, but it's still over 2 factorial, plus x to the 5th over 4 factorial. You get the idea, right? And then what we're doing here is saying x to the 2n times x to the 1st. So we have negative 1 to the n times x to the 2n plus 1 over that even factorial. So the series for x cosine x is equal to the sum from 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n factorial. And the interval of convergence for all of these is still all real numbers. The only way that the interval of convergence can change is if you've done some calculus. If you've taken derivatives or integrals, maybe the endpoints could change. But these original sine and cosine intervals of convergence were all real numbers. So all real numbers. All right, sorry about the mess up in the middle there. Hey, we all make mistakes. That's why it's important to remember and memorize these better than I have done.